3. Hello, this is Dr. Deepal Parekh. We are joining Dr. Paul Wagner once again for the uh, YouTube channel Wagner on Ethics and Leadership, discussing personality of mathematics. This is part 2. For part 1, please see the description below for the link. Dr. Wagner, during the last session, you explained features of the personalities of mathematics. Now, could you talk about how the heroes of math identify, and can you give some examples, please?
Yeah, absolutely. The heroes of mathematics, I think, are identified first and foremost by their uniqueness among us. They, in so many ways, just aren't like the rest of us. Um, they have a sort of a mystical quality about them. They're looking beyond just applications of math to different projects in the material world. They're lured into the uniqueness of mathematical structure itself. There have been people like Stanislaw Dehaene, who does a lot of studies of brain mechanisms and mathematical understanding. But even Dehaene can't distinguish between the ordinary person who becomes mathematically competent, an engineer, an accountant, many scientists, and those that reach for the stars within mathematics. There are several that we could think about. One, Leonardo of Pisa. He is the founder of what's called Fibonacci numbers. And what happened was Leonardo of Pisa before the Renaissance really began in Europe, he had heard of things going on down in the Mideast that was mathematically adventuresome. And so he wanted to go down and find out what the people in the Mideast countries were doing that was so different from what Europeans had clung to with their history of Greek mathematics. They didn't seem to have advanced much as the people in the Mideast had done, and that advancement in the Mideast was influenced by several things. I mean, when the Museum of Alexandria had copies of Aristotle's work and Plato and so many other mathematicians there, and that was all lost up in Europe, other than being passed down verbally from generation to generation. Also, Egypt had an acquaintance with folks to the further east, going all the way over to India, which had a very rich development of mathematics, pure mathematics, early on. So Leonardo of Pisa went down to the Middle East and discovered that they knew all sorts of things. He learned about algebra, which became algebra, and he learned about what we call Fibonacci numbers. He returns to Italy and begins talking about notions that other mathematicians in Italy had never given any thought to, and they were hungry for something new, and Leonardo of Pisa had much to give them, and so that began what we call the Renaissance. Historians usually describe the Renaissance, the European Renaissance, as beginning in Italy. Well, in a sense, it began with the mathematics that was brought to Italy from the Mideast. And as it moved up into the rest of the continent of Europe, it was mathematics driving it all and leading people in noble circumstances, as well as the monasteries of the time, to start reaching beyond what was just at the end of their own hands, their own arms, their own eyes, and trying to imagine what all else could be a part of this structure called mathematics. I mean, after all, they knew from Plato that some were so overwhelmed by mathematics, they figured it must be a part of an ethereal world above and beyond the world of sensuous experience. They had at least that much knowledge of what it could be. And then with the so-called dark ages, which really weren't dark ages, there was a lot of logic that developed during those so-called dark ages, and mostly in monasteries. But all this started getting drawn together in Italy as the riches of the Middle East, and then indirectly from India to the Middle East to Europe, began a new interest in mathematics that was incredible. One of the people at the time who also became famous uh, as the Italian Renaissance fertilized the rest of Europe was even women were who had been excluded from so much of the intellectual life of Italy, but women were becoming fascinated with mathematics. And it's interesting that one in particular was a nun. She was Maria Agassiz, and she was appointed by the Pope to the first professorship that a woman ever held anywhere in Europe. And it was at the University of Padua. And what was she teaching? Well, she was teaching and writing her own book of algebra, having heard of what had been created by Al-Jabbar down in the Mideast. So the first algebra book in Europe that was written by a European was written by a woman mathematician, Maria Agonazi, a nun. Another one that's very interesting, moving up from that, heroes of mathematics just allow the structure of mathematics to catapult them into almost mystical speculation. And I think we talked the other day about an India Ramajan, attributed his vision of theorems to encounters with the god Vishnu at night while he dreamed. But in Europe in the 19th century, there was an unusual guy by the name of George Cantor, and he started thinking about infinity. Infinity. Who thinks about infinity? And Cantor did, and we talked about infinite sets the other day. And Cantor, as I think I mentioned the other day as well, would do fabulous work in thinking about creations of set theory to account for one set being able to be enveloped by another, even though they would both have the same number of members in them. Well, Cantor wound up being put in a mental hospital from time to time because it put so much pressure on his mind, on his brain, to reflect about such matters that he would have these breakdowns, and then he'd come out, and as soon as he got out, he'd go back to mathematics again, and this cycle repeated itself from time and again. Then there's one other guy, and the other day that I mentioned about David Hilbert and his hotel, his imaginary hotel. David Hilbert, who is often said was the greatest mathematician moving from the 19th to the 20th century, and was also a close colleague of Einstein and another, probably the most famous woman mathematician ever, Emmy Noether. The three of them came together to help Einstein go from the special theory of relativity to the general theory of relativity. We'll talk more about that later, but I want to talk about just David Hilbert right now on his own. This great mathematician, thinking about infinity as well as other matters in mathematics. He conjured up this idea, and he said, imagine that there's a hotel with an infinite number of rooms. Okay. First of all, who thinks about that? But he did. Then next thing he tells us is imagine too that the rooms are all filled. So we have a hotel that has an infinite number of rooms, and the rooms are all filled. Okay, where are we going to go with this? He said, well, what do we do when a traveler comes by and he says, hello there, I would like a room in your hotel. What's the clerk going to say? Is he going to say, well, we're all filled? As we've said, it's an infinite number of rooms, and there's somebody in all the rooms. So that settles the matter, doesn't it? Well, not for Hilbert. He says, really, it's rather simple if you think about it. Here's all you have to do. And did I mention this the other day when we were talking about Hilbert then saying that what the clerk, so the guest comes in and says, the potential guest, and says, do you have a room? And the clerk says, well, of course. Well, how does that happen? Remember, you've already been told that it's a hotel with an infinite number of rooms in it. But you've also been told all the rooms are filled. And Hilbert says, well, this is the way it works. The clerk goes to the first room and knocks on the door and tells the residents there to pack up your stuff and move into room number 2. And then the clerk goes, or not the clerk, the bellman goes to the second door and tells the people there to pack up your stuff and move to room number 3. And then he goes to room number 3 and tells the people in room number 3, pack up your stuff and move to room number 4. And this continues infinitely. And so the traveler moves into that first room. Now, how many people can show up at the infinite hotel, infinite number of rooms and infinitely filled, and get a room in just that manner? And Hilbert says, as many as you like. Even an infinite number of new people can show up. Well, how can that be? Well, because an infinity never has an end. So even if we say infinity is filled, it's really something of a metaphor than an actual statement of material fact, because you can always add more to any infinite count. And so not only can we let the traveler in, we can let an infinite number of new travelers in. Just got to have the bellman go down and have everybody move up one. Who thinks about that sort of thing? Well, the superstars of mathematics. They've gone way beyond anything that we might talk about when we're talking about schooling people in arithmetic or algebra or anything such as that. They're going on to look at the structure of mathematics altogether. And there's one other person that we should mention too. He's a person that Einstein himself, when he was at the Institute for Advanced Studies at Princeton, New Jersey, Einstein would go from his home to the institute each day, and he'd walk along with the famous logician Kurt Gödel. And he was asked, what is why is it that you like? What is it that you like about the institute and in your morning walks with Professor Gödel? And Einstein said, the best of all is that I have the privilege of walking with Gödel to the institute, and that they would talk each day and upon a return. Well, Gödel pondered all sorts of things about what was the foundation of mathematics. So ranging from anything in speculations about infinities to linear and nonlinear calculi and imaginary numbers and so on. He pondered what could serve as a foundation to mathematics. And he said, let me take something simpler. Let's take a chunk of mathematics out and talk about how we could come up with a foundation for it. So he says, let's take a look at simple arithmetic. What could be a foundation for arithmetic? And after much pondering, he concludes, without a meta language outside of arithmetic to create the foundation, there is no way you can look at any area of mathematics, arithmetic or any other, and detail a foundation that will support the whole architecture of that area of mathematics from that point on. And this is called the incompleteness proof. And the incompleteness proof of Gödel is incredibly famous, and it's led to all sorts of people who are venturing into artificial intelligence and so on, puzzling over how could you ever create a foundation of mathematics for a computer to work with exhaustively, as a human being might, such as Kurt Gödel, if it's necessarily incomplete. And so those are some of the heroes of mathematics, and they just stand out from others. David Hilbert seemed fairly ordinary by comparison to some of these others. I told you about the mental problems that Cantor had. Kurt Gödel also had mental problems. Toward the end of his life, he had married a woman who had no education. She had been a waitress in a bar. And he suspected that people were trying to poison him, and so he'd only eat things that his wife would prepare for him. After Einstein died and Gödel was still alive, Gödel would only allow one former doctoral student of his to show up and visit him at his house. It was a Chinese mathematician by the name of Ha Wang. And Wang had was the only person allowed into the house, and Gödel's wife had died. Gödel was starving himself to death because he was fearful of eating. And Wang was able to round up some people to try to get food into or medical care into Gödel so that he would continue to live. And in that period of his life, Gödel tried to create a logical proof that God exists. So you see the kind of connections there to the most abstract imaginings that humans are capable of. They seem to be the kind of thing that lured the greatest of all mathematicians into the study of pure mathematics.
Wow. Wow. So when you mentioned the nun Maria Agassi being the I guess one of the first teachers of math. Can you algebra? Okay. Can you please define the word indoctrination, since it plays an important role in the early chapters?
Learning mathematics is, at the very least, learning another language. And just like whatever native tongue we learned from mimicking what we saw around us. We learned from adults and others that we trusted when they pointed out to us and gave us a sound to connect with what was visible to the young child and so on. That's how we picked up our languages. And then as we went through formal schooling, the activities that extended our language were more stepwise. But the idea wasn't just to create humans who could make sounds that matched up with a piece of the world. We wanted humans to be able to make sounds that allowed them to think about the world and then share with others their thinking about the world. Well, mathematics is a language. It just happens to be a very formal language that has no metaphors in it, has no ambiguous syncreties in it. And so very uniquely, it would seem to be in some ways a language that we could first formally model, and then if we wanted to go further with other languages that were not so logical as math, we could then extend our work into those areas. Well, it turns out that mathematics was more troubling to model than even our native tongue. We could get by with whatever we were picking up in our native tongue. But in mathematics, we use symbols that no one could see something connecting to the symbol. So what does 1 stand for? Well, you could use the numeral 1. You could use with Roman numerals, you could just use a slash straight down. You could use ONE to name a number. Where is that number that's named? Well, it's in the same place where the numeral is pointing to. It's at the same place where the Roman numeral slash is pointing to. Well, but we don't see anything there. So how is it that we learn to count? How is it that we learn to follow rules to join symbols together to get new symbols? 2 + 3 = 5. Now, initially, we just have to be indoctrinated in that. I mean, there is no role modeling or observation of the world that brings that sort of thing to mind. We find primitive tribes in in South America, today and elsewhere in the world. But anthropologists have found that even people who have been isolated from the rest of the developing world have counting skills that go beyond just quantitative bundling, because other animals, other species can recognize the difference between a bunch of and hardly any, or none at all. And they'll use their hands to count, the fingers, and a fist might mean a bundle of a certain sort. So even the most primitive tribes that can't visualize an association between symbols have symbols that they're using to engage in trade, to talk about other things in their lives. You can go back to cultures of all kinds, many uh, thousands of years ago, Mayans, people in India, people in China, astronomers noting things out in the heavens, tried to create a language that would allow us to advance those conversations, and we see them using numbers to do that. The Arabic numbers that we use today are just more economical than using, say, Roman numerals, but it's not as though they somehow have the right names for 1, 2, 3, and so on. So how do we put all that together? I don't know, but we know that to be able to talk about putting all that together, at first we just have to learn how to talk about it. In English-speaking countries, we learned how to use letters to talk about words, and then ultimately, after we talked about words, we talked about sentences and so on. But most of us, and certainly in the United States, we all learned the same song no matter where we grew up. And that was A, B, C, D, E, F, G, H, I, J. And little children just learned to recite those letters. Then after they had those letters in hand, we showed them how they could use them to name something, like a ball, tree, and then we started telling them that they could use these letters to name numbers. And then we started showing them what were numbers, and we told them, well, numbers are like this 1, this 2, this 3. And so we could say THREE, that's 3. What does it stand for? Well, it stands for that. And usually the kids don't even ask, so what's this? Well, that's 3. We use that to talk about like 3 oranges, and we use that to talk about 3 trees. And the kids usually don't ask any questions about why does that stand for 3 trees. We just, like the alphabet song, we just tell them that's the way it is. 3 comes after 2 and before 4. Why is that? Because that's just the way it is. And you can multiply 2 times 3 and you get 6. Well, why is it when you add them you only get 5? Because that's just the way it is. I don't think there's any other way of doing it. You've just got to be able to put the tools in their hands before you can talk about the use of the tools. Let me tell you what indoctrination is. A lot of political thinkers will have a lot of different things to say about it, but I try to keep it simple. Indoctrination is just causing someone to hold a belief for which they are unable to provide justification. So we give the kids the alphabet song so they can make words with the letters, and then we'll point from the word to something we want it to stand for. In math, we can't point to anything that the numbers stand for other than the word TWO stands for the numeral, whatever the numeral is pointing to. It's a 2, and then we can count things with that. But we're just telling the kids that's just the way it is. If the kid asks, why is it that way? There's few people in the world who are prepared to be able to explain to the kid why it is just that way. And if the kid stumbles on something as troublesome as 0, is 0 nothing? Well, no, 0 is still a number, but it's not like any other number. What's going on here? Fortunately, we don't have to deal with that with children for the most part. We just tell them this is the way it is. And there will come a time when we need to take them further. We will start teaching them somewhere along the line about geometry. Somewhere further on down the line, we might start teaching them about trigonometry. But all of it depends on initially just indoctrinating them, causing them to have beliefs about what happens when you put a plus sign between two numerals. What happens when you put an X that looks like multiplication between two numerals? Well, this is just how it's done. I can't imagine any other way of doing it. Now, teachers may say, well, we use these examples of like two oranges and two apples. How many pieces of fruit do you have together? And you have four. But two is not a property of those apples. Two is not a property of the oranges. Four isn't a property of all that fruit gathered together. 2 and 4 are properties of numbers, period. It just happens to be very advantageous for us to use numbers to talk about the world that's out there. But numbers seem to have their own reality. There's many mathematicians who confess that they're Platonists, and what they mean by saying that they're Platonists is that, like Plato, who thought there was a heaven of, perfect geometric form and of numbers and all those rules that went with it. The mathematicians of the day who confess to being Platonists are not telling us that they necessarily believe in that heaven, but they do believe that there is something non-material about numbers that can be true or definitively false. And that the pure mathematician is investigating those things. And at the frontiers of pure mathematics, there's still a lot to learn. And there are many false trails that people may stumble down. So that's what we're doing there with indoctrination. We're giving them the tools that they're going to one day need to do further investigations of math. When a child first goes to kindergarten, they're going to learn names of some of the other children there, and they don't ask, well, Cindy, why do they call you Cindy? Right? They just learn, her name is Cindy. Call her Cindy. Why? Because that's her name. That's as far as we need to go with that.
Who would have thought, or who knew math, subject like math is more than just a language of symbols?
Yeah. Yeah.
Um,
People that have written
so
about that and talked about it have always been separate and different from all the rest of us. And just extraordinary.
So, why do you think indoctrination is unavoidable in the early stages of mathematical learning?
Because we've got nothing to show the kid. We can't show them. Here's a 2. We can only show them we applied this thing we're calling 2 to 2 material objects. But even then, see, I've used the word 2 to say 2 material
Yeah.
objects. And yet we know 2 is not a part of those objects. But how do we circumvent that 2 is wholly abstract? It has no feel to it. It's nothing we can see, literally speaking. We can't smell it. There's nothing in our senses that selects 2 in the material world of experience in which we live. And yet we use 2 to talk about stuff in the world. We use mathematics sometimes to go beyond anything we've ever experienced in the world. And we come to conclusions about mathematics. And then we turn around and look at the world and go, my golly, that new item of mathematics that didn't seem to apply anywhere other than just as a consequence of our use of mathematics. But we've discovered it actually could be applied to a piece of the world. So math sometimes leads to discoveries of new things in the material world. But I don't think it's very common that new things in the material world lead to new discoveries in math, because math doesn't exist as stuff.
Yet it's an important part of anything, everything.
Mm-hmm.
Wow. Okay, perhaps the most important concept in your book, The Personality of Mathematics, is the concept of threshold. Can you please tell us about what the term means and why is it so important?
Yeah, I think threshold is probably the single most important concept to practicing educators and also to serious students. The concept of threshold means we're prepared to go through another step. You know, you walk up to a house, the door is closed, you're not going anywhere. But when the door is opened, you can step across the threshold and you're into a new environment. And I think that's the sort of thing that goes on intellectually as we first learn to count. Um, and then they just simply tell us, now here's how you add, here's how you subtract. Then we go further from that. We go to multiplication and division, and then we start learning some strange rules um, about what we can do. Multiply, divide, add, subtract, and we start learning some strange rules like this number of zero. If you multiply something by zero, you wind up with nothing. Well, why is that? Actually, getting to the point where you're asking that question, why is that? You've stepped across the first threshold, because before that, you've always been there just to be told this is what this means. The word banana split means this thing here. The word doggy means this thing here. The word 16 means the thing that's in between 15 and 17. Okay, it's all just clear. But once the student gets to the point where they go, oh, wait a minute, what this zero seems to do things that none of the other numbers do. Why is that? Ah, that threshold has been passed. And what are we going to say then? And presumably, one of the things we're going to have to say is that we have to confess that this number is so different from other numbers. And we learn in geometry to see that a whole lot of things that we thought we understood about numbers, we seem to have learned by looking at geometric arrangements. And they told us something about numbers, but how could that be? Geometric arrangements are also not things that exist truly in the world. Our triangles, our squares, our circles that we use are symbols that we use to represent the world or our thinking about the world. But it's not as though we have, like Plato said, we don't have a perfect circle in front of us. We don't have a perfect square. But as we look at the properties of squares and circles and lines and polygons, we start learning other things about how numbers can be collected together and how they might be used to describe something about the world, even though we know that the world that we're looking at in front of us can't be perfectly that way, but these numbers work out well enough to tell us about something we never even imagined before. Oh, now we're starting to get a feel for the applications of numbers. While we might also have a feel, certainly the ones that become the heroes, of the pureness of pure math as well. And they keep that in the back of their mind while they're initially caught up in, wow, this funny language allows us to talk about the world even though it's not a part of the world. It doesn't point to anything in the world. There is no two to point to. We come up with consequences like pi, irrational numbers. Uh, every school child knows that you can, the best estimate we have of pi is 3.14. But the students who are starting to catch on to arithmetic, to geometry, to the different areas of math, they start recognizing, wait a minute, did you say 3.14? But you said that's our best estimate. Why is that? Well, try to keep on doing your work here and seeing if 3.14 is where you stop. Well, no, you can add another digit to it. Well, yeah, keep going. Well, you could add another digit to it. Keep going. I can keep on adding digits. When does it stop? We don't know. We call it an irrational number. What does that mean? Well, it means that you can keep on repeating the operation forever, and there's no reason to believe it'll ever stop. Oh my gosh. Huh. But don't worry about it. I mean, 3.14 is good enough for anything you're likely to use, Jerry. But the kid who's actually stepping through the threshold, he's still pondering, why do we have irrational numbers? Let me get to high school and he's still pondering this thing about 3.14 or whatever. And before you know it, he starts thinking to himself, if he's going to pass through another threshold. I think I just heard a teacher say that between any two natural numbers, 4 and 5, that there's an infinite number of irrational numbers between them. And that irrational numbers is like pi. There could be an infinite number of numbers like that in between any pair of irrational numbers. I thought the irrational or the natural numbers were just next to each other. And then he told me you can kind of open it up and you put in fractions. Okay, I could buy into that. But then he started telling me about pi, and you really can't find it. It's in between 3 and 4. But you can't find out exactly where, because the operation that got you to 3.14 can be repeated infinitely, and you still won't be at the end. And now you tell me that there's an infinite number of numbers just like pi that are irrational numbers in between any pair of natural numbers. Oh man, that's just weird. And we've got more that we can keep on adding to it, right? Prime numbers. Whenever we look for, how many prime numbers are there? There always seems to be another one. The computers, when they're on downtime, no one's running much on them, and so they've got time to just run an equation over and over again. Seem to find, maybe after years of just running the equations, finding another prime out there. How far do the prime numbers go? When we look in the stars and we look in the heavens, we at least have some end to that. We can talk about really big numbers when we look at the universe. But if somebody asks us, how big is the universe, we can give an estimate of that by looking both at, what we know about the origins of the universe, which is a little shaky. But then we look at the speed at which things seem to have gone from there, and that's how we got the Big Bang Theory. And the Big Bang seemed to lead to celestial dust, which we call planets, slowing down as it goes out. And then in recent years, we've found out that sometimes there's even patches of that slowing down, turning around and being faster, and then slowing down again. We don't know why that is, but we can imagine, for good reason, using mathematics once again, that our universe can't be any bigger than the effects of gravity on all of those particles that are drifting apart. Because once you get to the end, there's nothing, there's nowhere else for them to go. And so they're just there. If we use light, which is the fastest thing we know of in the world, Einstein's the speed of light is certain, it's absolute. Nothing goes faster than it. If we use the speed of light to measure how big the universe is when it gets to that end point, we'll be able to shoot that light beam out there beyond our universe to see if there's any other universe. Well, right now, notice, doesn't seem to be any way that we can do that. Why not? Well, because as that beam of light begins hitting the edge, getting to the edge, gravity's going to pull it back in. And so all the space within our universe is curved, from the tiniest distance to the largest distances. We can't find out what's out there. Wow. So why not? In any case, mathematics leads us to things to ponder in our material world that's beyond any of our sensuous abilities at the time. On the other hand, the world itself tells us nothing about mathematics. Even when we come up with a new mathematical tool, that's built upon the foundations of math, not upon the foundations of the world. In any event, thresholds, the really skilled teachers, the people that ultimately bring all of humanity together in conversations about what exists and doesn't exist, and everything that matters to human beings. They are taking us through a sequence of indoctrination to a threshold that's full of questions, and we speculate and we share, and then we reach the limit where we have to confront indoctrination of a new sort. Now we're going to start doing trigonometry. Oh, what is that? Well, let me tell you. And so, we have to go through a period of indoctrination again. If it's successful, then one of the things that happens is there's a new threshold. We've opened up a new door. We get to join the great conversation of humankind at a higher level. And if that continues again and again, where does it end? I don't know. I kind of think of perhaps one of the highest levels that ever reaches. I think of Einstein walking with Gödel. And those two guys walking along, talking about the things they talk about that others of us can't even imagine. Even our best scientists talking about the world itself may come to a limit before they get to the level of imagination that an Einstein and a Gödel might share with one another, participating at the highest level of the great conversation of humankind as they walk to work each day at the Institute for Advanced Studies in Princeton.
So do you think when we talk about today's teachers, can teachers be doing moral wrong by excess indoctrination and failure to recognize when students understand our understanding has crossed the threshold?
Absolutely. Indoctrination is a very potent mechanism. The Chinese communists of the 1950s in their re-education camps had a phrase that they used, and it was that they believe that you put anybody in a re-education camp, you can make them different. It's very much like George Orwell's 1984. Anyhow, the phrase of the Chinese communists was, if you throw enough mud at a brick wall, some wood is bound to stick. Teachers who abuse their indoctrinative strategies don't bring the students to the next threshold. They leave them on the doorstep outside. And we don't ever want to do that. If you leave them at the doorstep outside, they're never going to learn more about the depth of math, nor are they going to learn even more about the application depth of math, because they're standing outside in the cold. You said, this is all you need to learn. It just is what it is. We got to do that for a while, but that's only to get the door open so they can step through the threshold.
Thank you, Dr. Wagner. This concludes our part 2 of the discussion on the book, The Personality of Mathematics. Thank you so much for this intense conversation, Dr. Wagner. We have one more part that we will be recording to conclude the book. If you enjoy this content, please share and subscribe to the channel, Wagner on Ethics and Leadership. Thank you so much. And thank you so much, Dr. Wagner, for your time and sharing the knowledge and the wisdom. Thank you.
And thank you, Dr. Patrick.